Alright, we're in unit number 6 still, energy. We're on page 9 of your notes. We're going to work through example number 4. Example number 4 is another application of the law of conservation of energy, and then we'll run through a couple of the demonstrations I've got down here that I can still do on video. The rest of them I have to do in class. Alright, Sergei Bubka is the world's greatest pole vaulter. He has since retired a while ago, but he holds 17 of the top 18 vaults ever recorded, and that is still accurate to this day. He is head and shoulders above everybody else that's ever tried it. And I want to say he retired, I don't know, maybe at, right around 2000. I don't know. It's been a number of years ago since he's retired, and nobody's ever approached what he's been able to do. So the question is what height can Bubka vault if he approaches the vault at 10.3 meters per second? I think Sergei competed for the Ukraine, if I'm, and maybe Soviet Union, and there was, the Soviet bloc kind of changed there in the late 80s, early 90s, and I think he switched nationality there in the process. But what we're going to do is we're going to use conservation of energy to calculate how high he can actually vault if he approaches the mat at 10.3 meters per second. And then once we finish this one, there's a couple interesting points that I'll try to draw out as we go through this. All right, so every time that we do the conservation of energy, you got to have a sharp pencil. And I am way low on pencils here. Here's one. We'll try this guy. All right, so conservation of energy, EO equals EF. And let me draw a quick diagram over here to kind of get us started. So here's kind of what's going on. Here's the bar he's trying to vault over, and here's Sergei here, my wonderful stick figure. So here he is with his pole vault and his pole. All right, so he's going to run in, and then he's going to, here he is here, stick it in the ground, and then here's his head here, and then try to get over. All right, so we have to choose, when we do this, we have to choose a starting point and ending point. Really, it doesn't, in all reality, it doesn't matter where you start, but in terms of doing the problem, you do have to be kind of sensitive in terms of where you start and where you stop the problem, because usually one way is going to make it a little bit easier. And we're going to start when he first jams the pole into the box down here. So that'll be the beginning, and then the end is when he's right here at the very top. So he's just basically getting over the top there. All right, so let's start to talk about the beginning. So we're doing conservation of mechanical energy. On the previous page, we talked about the 4 types of energies that we're going to have. So let's talk about these real quick, because these can be confusing on this particular problem. All right, so we have to, at the beginning, figure out which one's he at. Does he have kinetic? Yeah, because he's in motion. So I'm going to go ahead and put down kinetic. Does he have gravitational? No, he doesn't have any gravitation because his feet are still in the ground. Does he have spring or elastic potential energy? Now here's where it gets to be tough. The answer is no. And the reason for that is, I think the reason that some people say yes is because they see the bar, and the bar is bent. And I would agree he would have elastic potential energy if the bar was bent, or while it's being bent. But as soon as he jams the bar in the box, the bar's not bent yet. So the question is going to start right when he jams in the box, right before the bar begins to bend. Okay, does he have rotational kinetic? No, he's not really spinning. Okay, so don't have to worry about that. You could argue that he's kind of rotating up through, but we're going to keep it simple. So at the beginning, he only has kinetic. So let's put that down first. So you've got kinetic energy here. So really the beginning is when the bar is still straight here, kind of right there. Okay, now the next part is, this is the end. We're going to start, this is the beginning, and then this is the ending part of the problem. So we have to figure out, well, what forms of energy does he have up there? And we're going to have to make a little assumption at the top. We're going to have to assume, even though this isn't totally true, it's pretty close, and if we don't make this assumption, it's going to make the problem really tough. We're going to assume that he's basically at rest at the very top. It's a close assumption. It's not perfect, but it's close. So we're going to say he has, at the top, no kinetic. At the very top, he will have gravitational because he's above the ground. he won't have any elastic because at the very top the bar is straight. So all the elastic potential energy occurred between the time of the beginning, between the beginning and the end. So we really don't have to, since we're only concerned about the very beginning and the very end, we're not concerned about the middle. We don't have to worry about the kinetic or the elastic potential energy stored inside the pole. The other thought is this: any energy given to the pole is given back. I said it this way: any energy given to the pole at the beginning. So if I'm here, any energy given to the pole at the beginning, like right here, is given back up here. So all of that energy is conserved. So you want to kind of think of it that way as well. So let's go back over here then. So we've got gravitational, yes. Kinetic energy, or elastic potential energy, no. Rotational, no, not really. So the only thing we have at the end is going to be gravitational potential energy. So let me come over here and we'll slip in gravitational potential energy. And then we'll zoom in. We'll just go ahead and use our equation. So we got an equation for kinetic, which is 1/2 mv squared equals gravitational mgh. And then the masses cancel out. So you know that the mass, once he's going, once he vaults, the mass doesn't really matter in this case. Obviously, he's got to have the strength to pull him up on the bar, but that's something different. Okay, we want to know height, so we're going to solve for h. So h is equal to, what do we got? We're going to divide by g, so we get v squared over 2g. You might want to verify the algebra. It's correct, but you want to verify it for yourself that that is correct. And then h is equal to, v squared is going to be 10.3 over 2 times 9.8 meters per second squared. All right, so let's see what we got here. So we're going to do, let's see if I can squeeze this in there. There we go. So 10.3 squared, whoops, 10.3 squared, there it is, divided by 2 and then divided by 9.8. So we're going to go h is equal to 5.4, and that'll be meters. So that's how high, if he was coming at 10.3, that's how high he could jump. Now, if he actually, I think his world record is right around 6, so you know, obviously he was traveling a little bit faster, but you get the idea that if you look at this, the height that he can jump is only dependent upon really 2 variables. The acceleration of gravity, which he has no control over, and then his speed. And notice his speed is squared. So a little increase in speed gives you a dramatic increase in the height. I got this problem actually off of a former professor of mine, and he too was a track coach, and he actually went to go see Sergei Bubka compete. I think it wasn't just to see him, but it was to see the rest. I think the world, I don't know, some Pan Am Games or World Championships were held here in the United States, and he went to go watch. And he said he had a front row seat for the pole vault, and he would watch all the competitors go by on the pole vault when they would run down and then jump. Well, there was a stark difference between the speed with which Sergei Bubka ran down the runway and the speed of all the rest of his competitors. His speed was by far faster than all the rest of his competitors. And if you look at this equation, you can definitely see, gosh darn, a little bit more speed is going to give you some drastically positive results in terms of the height that you're going to be able to vault. I noticed the same thing. I coached a kid when I was coaching in Springfield. He didn't vault, but he high jumped. And high jump is, the concepts and the physics principles are much in the same way. You basically come in with a lot of kinetic energy and you're going to transform that to gravitational. Well, if you just stand below the bar, no approach, just stand below the bar and try to jump, well, there's no kinetic energy to be, or I should say very little. You can generate a little bit because you can bend your knees and then, but outside of that, there's very little kinetic energy to transform into gravitational. And Ryan happened to be a pretty good sprinter. And what he would do is he would take his sprinting speed and approach the bar at the highest speed he could do and still maintain some composure at the bar, and then convert his kinetic into gravitational. What was interesting was I think he was all of 5'8", 5'8". Usually high jumpers are pretty tall, but he was just 5'8", and he could high jump 6'9", over a full foot over his head. And he had some God-given ability. He really could jump really well, but also he was fast, and he learned how to transform his kinetic energy into gravitational potential energy. And as his coach, I would watch him, and I would notice that if he didn't have a lot of speed going into the jump, so when he got to the bar and he was about ready to jump, if he didn't have a lot of speed built up, chances are he's not going to be able to jump real well. He's going to miss. But if he had a lot of speed and it was controlled speed, chances are he's going to get over it. And he was a fun kid to coach, and just did a really great job. So that's example number 4. I'd like to run through, I think, 2 of these examples down here. Demonstration, half rubber ball. I think some of you may have seen this. Basically have a racket ball that's been cut in half, and if you take this and flip it over, and then put it on the ground and give it a little bit of time, it'll literally pop up on its own. And I know you couldn't see that, but it basically popped all the way up to the ceiling, almost came within maybe a couple inches of the ceiling. So the question is where does it get all that energy from? Well, because it gains gravitational, it gains some kinetic. So when I pinch this in, I'm storing inside some elastic potential energy. And then when I put it on the ground, see if I can do this. Ooh, I'm getting a rip in that. That's not good. I have to get a new one of these. When I put it on the ground, and I bet that rip, this is on video, I've never noticed that rip. Can you see that rip in there? Let's see, try one more time. Let's see if it stays. But it doesn't. There we go. Alright, so it converts basically the elastic potential energy into kinetic, and then kinetic all the way into gravitational. Alright, so that's one. The other one I want to talk about is a jar of sand. Now, I'm not going to actually do this one. I'm just going to talk about it. This is one we'll actually do in class. I've got basically a bottle of sand, just a bunch of sand inside of here. And what I do in class is unscrew the top of this, put a thermometer in here, and just let it sit for a while. Let it all come to room temperature, and then get the temperature of that, and then pull the thermometer out, close this off, and then I'll give it to every kid in the classroom and have them just shake it for 5 seconds. Pass the next kid, shake it. And when they come back, they're going to notice, what we'll do is we'll open it up, put the thermometer back in, and we're going to notice that the thermometer will have risen. And it's risen for 2 reasons. The reason that we're trying to analyze is the fact that when you shake it, that's mechanical energy. It's kinetic energy. And that kinetic energy gets transformed into thermal energy. And so we can see evidence of that thermal energy on the thermometer. Temperature has risen. And another reason that it will have risen as well is just by the sheer fact that kids are holding it, and their body temperature is going to cause temperature of this to rise as well. But anyway, it's a good example of showing another example of a transformation of energy. And I think that's it. So that's example number 4. On the next video, we'll take a look at example number 5.